Well, welcome back, everyone. What I want to do now is start a series of lectures talking about the concept of confounding. So the first thing I think we need to do is to develop a definition of confounding. And let's do this first conceptually, and let's do it with an example. Let's suppose we're going to do a cohort study. Now, we know about cohort studies. You've talked about them. You've been using one in your analysis data set. The Framingham heart study is an example of a cohort study. So let's imagine you're doing a cohort study like Framingham. You want to know whether smoking increases your risk of developing heart disease. So what you do is you enroll a bunch of smokers in your cohort study, a bunch of non-smokers. You follow them over time to see who develops heart disease and who doesn't. You measure incidence of coronary heart disease among the smokers, among the non-smokers, and you combine them into a measure of association like a risk ratio or a rate ratio. So let's suppose you do that. You analyze your data, and you saw the following results. That when you compared your smokers to your non-smokers in this cohort study, you saw a risk ratio, if you want, maybe a rate ratio of 2.0. The incidence of coronary heart disease was twice as much among the smokers than among the non-smokers. So now you want to write a paper, and you want to tell in your paper, describe the effect of smoking. You'd like to say, not only did I measure this association, risk ratio equals 2, but I'd like to say something like smoking doubles your risk of getting heart disease or doubles the rate of getting heart disease. I want to make a causal statement. But remember what I said a few times in this class. Whenever we measure an association between a risk factor and an outcome, before we can conclude that that association measures the true effect, the causal effect of that risk factor on the outcome, we have to exclude alternative explanations. We have to rule out the role of bias, the role of confounding, and the role of chance. And we've been referring to these three alternatives a few times when we've looked at the various study design options and the examples we've discussed in this class. Well, in this series of lectures, I want to look at the middle alternative explanation, the potential for something called confounding. So let's suppose you did your study. You found this risk ratio, rate ratio equals 2.0, but then you look closely at your data. And you notice that the age distribution of your smokers was not the same as the non-smokers. Let's suppose that the smokers in your study are much older than the non-smokers. So really what you found was twice the incidence of heart disease among old smokers compared to young non-smokers. And now the question is, how do you interpret that risk ratio of 2.0? Is it reflecting the effect of smoking? Is that the reason we saw this twofold increase in the incidence of heart disease? Or was it because the smokers were older and older age increases the risk of getting heart disease? Or might it have been due to both? The fact that the smokers not only smoked, but they're also old. Those are three possible interpretations of that measure of association that we found in this data set. Well, before we go further with this example, let's just review in our minds what we think the true causal effect of a risk factor is. The ideal study I'd love to do to measure the true effect of smoking on heart disease, whether smoking causes heart disease and what its quantitative effect is, I'd love to do the following. I'd love to take a group of people, have them smoke, follow them for 10 years or so, measure their incidence of heart disease, and then go back in time, take that same group of people, make sure they don't smoke, and follow them for 10 years to see how much heart disease. What I would be measuring are counterfactual outcomes. This is what we talked about at the beginning of this course. What would happen to a person, or in this case a group of people, under two different scenarios? One when they're smoking and the other when they're non-smoking, but it's the same group of people. So any difference in outcomes for the same group of people measured under identical situations, except in one situation they're smoking, in the other situation they're not smoking, any difference in those outcomes really must be measuring the effect of smoking on that outcome. That's what we love to do. Well, we can't measure these counterfactual outcomes. I can focus on my smokers in my data set, and I can see what really happens to them because they smoked, what their incidence of heart disease is. What I don't have in front of me is what would happen to those same smokers had they never smoked. Well, we've talked about this before. The way we epidemiologists resolve that problem is we estimate the counterfactual outcome among the smokers by using some non-smokers. Those non-smokers will estimate what would happen to smokers if they hadn't smoked. That's the whole purpose of epidemiology. But to be able to say that the non-smokers reflect what would happen to the smokers had they not smoked requires that the non-smokers be what we call exchangeable to the smokers. Meaning that if I look at the non-smokers in my study, what they are really going to give me is an estimate of the counterfactual outcome, what would happen to the smokers had they never smoked. And likewise, if I looked at the smokers, their actual outcomes would estimate what would happen to the non-smokers if they had in fact smoked. So exchangeability means the two groups I'm comparing, the smokers and the non-smokers, essentially can be switched, can be replaced. Each of them is showing what would happen to the other group had that other group either had or not had the exposure. The non-smokers describe what happened to the smokers had they never smoked, and the smokers describe what happened to the non-smokers if they ever did smoke. Well, remember randomized controlled trials. I said that's a place where we can probably argue that the two groups we're comparing are exchangeable because people were assigned to these two groups randomly. The type of person in the treated group getting a new treatment is very similar to the type of person assigned to the comparison group in a randomized trial. But what about in cohort studies like this? Are the two groups comparable? If so, their outcomes are exchangeable, and if so, our measure of association, risk ratio equals 2, would reflect the true causal effect of the risk factor. So taking that one step further, exchangeability in epidemiology means the two groups you're comparing are comparable. The non-smokers look just like the smokers in every detail that the smokers have, except that they don't smoke. Well, what do you mean by every detail? Every other risk factor, every other determinant that could cause the outcome is balanced, is the same among the non-smokers and the smokers. That's what comparability means. Comparability with respect to other risk factors, other determinants of the outcome. And lack of exchangeability means we don't have comparable groups. That's what we conceptualize to be this notion of confounding. So let's go back to your cohort study. I told you your non-smokers are younger than the smokers. Therefore, the non-smokers are not going to estimate what would happen to your smokers had they never smoked, because the non-smokers differ from the smokers in two regards. They are not smoking and they are younger. Both of those factors influence the outcome. We want our non-smokers to reflect what happened to our smokers if they never smoked. And the problem is what our non-smokers are telling us is what would happen to young smokers had they never smoked. They're not telling us what would happen to our old smokers in our data set if those old smokers had never smoked. So the problem is the non-smokers we have are going to estimate what would happen to the smokers if they never smoked, because they're estimating they're under accounting for the effective age. They are young compared to our smokers. That implies our risk ratio that we observe in our data set, the doubling of the incidence of disease, is really reflecting the mixture of two effects. Our exposed people are smoking, and smoking increases your risk of disease. Our exposed people are older, and older age increases your risk. Now you can describe everything I said in terms of a picture. This is a causal diagram, something we call a directed, meaning it has arrows connecting risk factors to outcome, acyclic, because these arrows don't loop around, but it's a causal graph. And that's what we call a DAG, a directed acyclic group. It's showing that we suspect that smoking might have a direct impact on the occurrence of coronary heart disease. That's the reason we're doing the study. That's what we want to measure. But the problem in our data set is that there's another mechanism that could explain why the smokers are getting more heart disease than the non-smokers. There's this other factor, age, that's having two properties. It's related to smoking. I told you your smokers are much older than your non-smokers. We anticipate that old age also increases your risk of developing coronary heart disease. So what this causal diagram is showing us is that there's two pathways by which smoking could be linked to the outcome coronary heart disease that could explain our measure of association of risk ratio equal to 2.0. These two pathways that I'm referring to is the direct pathway, linking smoking directly to your risk of developing heart disease, and what we call this backdoor pathway that goes through age. So we don't know whether our risk ratio equal 2 is reflecting the influence of the direct pathway, that top arrow, or this backdoor pathway that goes through age. So that backdoor pathway is reflecting the non-comparability. It wouldn't exist if the smokers and the non-smokers had the same age. There'd be no link between age and your exposure status. So if you want to make a conceptual definition of confounding based on this non-exchangeability principle, essentially in terms of a graph, confounding means a backdoor pathway exists. That's the concept of confounding. So hopefully we agree with this. Now we have to take it a step further. We have to develop a working definition of what confounding is and a method for detecting it in a data set. And that's what we'll do in the next lecture. So I'll see you then.